On November 28, 2025, astronomers around the world continue to study something puzzling in our solar system. It is called 3I/Atlas, and for years, scientists have been watching it carefully, trying to understand what it really is. But here is the strange part. The more we learn about this visitor, the more questions pop up. What if the thing we have been tracking is not what we thought it was at all? What if we have been following a decoy, something that broke apart or changed completely since we first spotted it? Stay with me, and we will walk through one of the most curious mysteries in space right now. We will talk about what 3I/Atlas is, where it came from, why scientists are so puzzled by it, and what the latest research tells us. Along the way, you will see how hard it is to study something so far away and so strange. And by the end, you will understand why this little visitor is teaching us so much about the universe beyond our own backyard. Let's start at the beginning. In December of 2024, a telescope system in Hawaii called ATLAS spotted something new. ATLAS stands for Asteroid Terrestrial Impact Last Alert System, and it is designed to watch the sky for objects that might come close to Earth. When ATLAS noticed this new dot moving across the stars, astronomers got excited. They started tracking it carefully, measuring its speed and direction. What they found was surprising. This object was moving in a strange path, one that did not match the usual orbits of comets or asteroids that belong to our solar system. Most objects in our solar system move in patterns that match how they were born. They circle the sun in paths shaped like ovals, and they stay within a certain area. But 3I/Atlas was different. Its path looked like it came from somewhere else, from the space between the stars. That is when astronomers realized they might be looking at something very special, an interstellar object, a visitor from another star system. Now, before we go further, let's talk about what interstellar means. Interstellar is just a fancy word that means between the stars. Our sun is one star, and there are billions of other stars in our galaxy. The space between these stars is enormous, so enormous that it takes light years to cross it. A light year is the distance light travels in 1 year, and that is about 9.5 trillion kilometers. When we say something is interstellar, we mean it traveled across that huge empty space to reach us. 3I/Atlas would be only the third interstellar object we have ever confirmed. The first one was called 1I/Oumuamua, discovered in 2017. The second was 2I/Borisov, found in 2019. The number at the start tells us the order they were discovered, and the I stands for interstellar, so 3I/Atlas means the third interstellar object, discovered by the Atlas system. But here is where things get tricky. When scientists first started studying 3I/Atlas, they thought it might be a comet. Comets are like dirty snowballs in space. They're made of ice, rock, and dust, all frozen together. When a comet gets close to the sun, the heat makes some of that ice turn into gas. The gas escapes and carries dust with it, forming a glowing cloud around the comet called a coma. Sometimes the pressure from sunlight and particles streaming from the sun push that gas and dust into a long tail. That is why comets often look like they have bright tails stretching behind them. Scientists expected 3I/Atlas to show these signs. If it was a comet from another star system, it should have ice inside it. As it travelled closer to the sun, that ice should start to melt and create a coma and maybe a tail. And for a while, that is exactly what seemed to happen. Observers saw a fuzzy cloud around it. But then something strange occurred. The object started to fade. Not slowly, like you would expect as it moved away from the sun, but suddenly. It got dimmer much faster than anyone predicted. Some telescopes could barely see it anymore. Other observatories that tried to take pictures found nothing where the object should have been. It was like 3I/Atlas just disappeared, or broke into pieces too small to see. This is where the decoy idea comes in. What if the bright thing we saw at first was not the main object? What if it was just a cloud of dust and gas, and the real solid piece, the actual nucleus of the comet, was hidden inside? Or what if the whole thing fell apart, crumbling into thousands of tiny fragments that scattered in different directions? When something like that happens, we might keep tracking the brightest piece, or the biggest cloud, but that might not be the original object anymore. We might be following a decoy without realizing it. Let's take a step back and think about why this matters. Understanding 3I/Atlas is important because interstellar objects are incredibly rare. In all of human history, we have only confirmed 2 before this one. These visitors give us a chance to study material from other star systems without ever leaving our own neighbourhood. Every measurement, every photograph, every little detail we learn helps us understand what is out there in the galaxy. But if we are tracking the wrong thing, if we are following a cloud or a fragment instead of the main body, then our measurements might not tell us the truth about what 3I/Atlas really is. Scientists use powerful telescopes to study objects like this. They look at the light coming from the object and break it into different colours, kind of like how a prism splits sunlight into a rainbow. Each colour tells them something. Certain colours mean there is ice. Other colours mean rock or metal. By studying these colours, or what scientists call a spectrum, they can figure out what the object is made of. But if the object breaks apart, the light changes. Suddenly you are looking at light bouncing off dust instead of light from a solid surface. The information gets messy and hard to read. Now picture this. Imagine you are trying to study a snowball flying through the air. At first it is solid, and you can see its shape and measure how big it is. But then it starts to melt because the sun is shining on it. Water drips off and evaporates. Bits of ice break away. Soon, instead of one solid snowball, you have a cloud of water vapour, droplets and ice chunks all spread out. If you only looked at the brightest part of that cloud, you might think the snowball is still there, but really it has fallen apart. That is similar to what might have happened with 3I/Atlas. Researchers have been trying to answer the big question. Did 3I/Atlas break apart, or is it still intact somewhere, just too faint for us to see easily? To figure this out, they look at how quickly it faded. They compare its brightness over time, taking measurements every few days or weeks. When they plotted those measurements on a graph, they saw a steep drop. The object got dimmer much faster than a normal comet would. That steep drop is a clue. It suggests something unusual happened. One idea being tested is that the nucleus, the solid icy core of the comet, shattered into many pieces. When a comet nucleus breaks apart, each piece is smaller than the original. Smaller pieces have less ice, so they produce less gas and less brightness. If 3I/Atlas broke into 10 pieces or 100 pieces, each one would be fainter than the original. Together they might still reflect some light, but not enough for our telescopes to spot from so far away. The object would seem to vanish. Another possibility is that 3I/Atlas was always very fragile. Some comets are held together loosely, almost like a pile of gravel with ice acting as glue. If the ice melts, the gravel falls apart. Scientists call these rubble pile comets. If 3I/Atlas was a rubble pile, it might have crumbled as soon as the sun's heat reached it. That would explain the sudden fading. The heat broke the glue, the pieces scattered, and the brightness dropped fast. There is also a third idea, one that is a bit more surprising. Maybe 3I/Atlas is not a comet at all. Maybe it is something else entirely, like an asteroid covered in ice or dust. Asteroids are rocky objects without much ice. They do not usually create comas or tails, but if an asteroid travelled through space for millions of years, it might collect a thin layer of ice on its surface from freezing gases in the cold of interstellar space. When that asteroid got close to the sun, the thin ice layer could melt away, creating a brief cloud that made it look like a comet. Once the ice was gone, the cloud would disappear, and we would be left looking at a plain, dark rock that is much harder to see. Scientists have not settled on one answer yet. That is part of what makes this so interesting. They are still gathering data, still comparing ideas, still running computer models to see which explanation fits best. Let's talk about what we know for sure, the facts that astronomers have confirmed. We know that 3I/Atlas was first detected in late 2024. We know its path through space does not match objects born in our solar system. Its orbit is hyperbolic, which means it is not travelling in a closed loop around the sun. Instead, it is on a one-way trip. It came in from interstellar space, swung past the sun, and is now heading back out. It will leave our solar system and keep going forever, unless something very unusual happens. We also know that when it was first observed, 3I/Atlas showed signs of activity. There was a fuzzy coma around it, which meant gas and dust were escaping. This activity made it bright enough to spot with professional telescopes. But as weeks passed, that brightness faded quickly. By early 2025, the object was much harder to see. Some observatories reported losing track of it entirely. Records show that the object was travelling at about 34 kilometers per second relative to the sun when it entered the inner solar system. That is incredibly fast, more than 120,000 kilometers per hour. At that speed, You could travel from New York to Los Angeles in less than a minute. This high speed is another clue that 3I/Atlas came from beyond our solar system. Objects that belong to the Sun do not usually move that fast unless they get a gravity boost from a planet. Now let's think about where 3I/Atlas came from. Tracing its path backward, astronomers tried to figure out which direction it arrived from. They used its speed and orbit to point back in time, like rewinding a movie. The calculations suggest it came from a region of the sky in the direction of a constellation we call Ursa Major, also known as the Big Dipper. But that does not mean it came from a star in that constellation. It just means that is the general direction it was travelling from when it entered our solar system. Interstellar space is mostly empty. The distance between stars is so huge that even travelling at 34 kilometers per second, it would take 3I/Atlas thousands or even millions of years to cross from one star system to another. During that time, it floated through the cold darkness, far from any sun's warmth. The temperature out there is close to absolute zero, about minus 270 degrees Celsius. That is cold enough to freeze almost anything. While 3I/Atlas drifted through that cold, any ice on its surface would stay frozen solid. No melting, no activity, just a silent frozen chunk moving through the void. But once it got close to our Sun, everything changed. The Sun's heat started to warm it up. If there was ice inside, that ice would begin to turn into gas. Pressure would build up, inside cracks and pockets. Sometimes that pressure is enough to crack the object apart, like when water freezes inside a rock and splits it open. Scientists think this process might explain why 3I/Atlas faded so quickly. The object might have held together for millions of years in the cold of interstellar space, but the sudden warmth from the Sun could have been too much. Thermal stress, the term for damage caused by temperature changes, might have shattered it. Think of it like taking a frozen glass and pouring hot water into it. The glass can crack because one part heats up faster than another. The same thing could happen to an icy comet. Here is where the story gets even more interesting. Some researchers are looking at the possibility that 3I/Atlas is part of a larger group of fragments. Maybe a bigger comet broke apart long ago, and 3I/Atlas is just one piece of the debris. If that is true, there could be other pieces out there, travelling on similar paths. Some might have already passed through our solar system without being noticed. Others might arrive in the future. This idea is being tested by searching old telescope images. Astronomers are checking pictures taken months or even years before 3I/Atlas was discovered, looking for anything that might have been missed. Sometimes a faint dot in an old photo turns out to be important once you know what you're looking for. If they find other objects on similar orbits, it would support the idea that 3I/Atlas is a fragment. Now, let's talk about the tools scientists use to study these objects. Telescopes come in many types. Some telescopes collect visible light, the kind of light our eyes can see. Others look at infrared light, which is heat radiation that warm objects give off. Infrared telescopes are especially useful for studying comets, because the dust and gas around a comet glow brightly in infrared. Even when a comet is too faint to see in visible light, it might still shine in infrared. One of the challenges with 3I/Atlas is that it became too faint too quickly. By the time some of the biggest telescopes tried to observe it, there was not much left to see. This is frustrating because the more data scientists collect, the better they can understand what happened. Missing data means missing answers. Despite these challenges, researchers have learned a lot. They have measured the object's rotation. Like most objects in space, 3I/Atlas spins as it moves. By watching how its brightness changes over time, scientists can figure out how fast it spins and what shape it might be. If an object is shaped like a potato, it will look brighter when the long side faces you and dimmer when the narrow side faces you. The pattern of bright and dim tells you the rotation speed. For 3I/Atlas, the rotation measurements were tricky because the object was fading. Brightness changes from rotation got mixed up with brightness, changes from the object breaking apart or losing gas. But scientists did their best to separate these effects. They found that 3I/Atlas might be spinning every few hours, which is fairly typical for a small comet. Let's pause for a moment and think about what this all means. We have an object that came from another star system, travelled across the galaxy for who knows how long, entered our solar system, started to break apart or fade away, and is now leaving, possibly as a cloud of fragments. We got a brief glimpse of it, just a few months to study it before it became too faint, and in that short time, scientists had to gather every bit of information they could. It is like trying to take a photograph of a shooting star. You only have a second or two before it is gone. This is one reason why astronomers want better detection systems. The Atlas telescope that found 3I/Atlas is part of a network designed to spot dangerous asteroids before they hit Earth. But it also finds objects like this, rare interstellar visitors. The more telescopes we have watching the sky, the better our chances of catching these visitors early when they are still bright and easy to study. Another tool that helps is computer modelling. Scientists can create simulations on computers that show what might happen to a comet under different conditions. They can test ideas. What if the comet is made of pure ice? What if it is half rock and half ice? What if it is a rubble pile? Each scenario produces different results. By comparing the simulation results to the real observations, scientists can narrow down which scenario is most likely. For 3I/Atlas, computer models suggest that a fragile, loosely held together structure fits best. A solid chunk of ice and rock would not fade so quickly, but a rubble pile, or an object with lots of cracks and weak spots, could crumble under the stress of the sun's heat. The models also suggest that even small amounts of gas escaping from the surface could push fragments apart, making the breakup happen faster. Now imagine if 3I/Atlas did break into many pieces. Where are those pieces now? Are they still travelling together in a loose group, or have they spread out across space? If they are still together, we might be able to find them with sensitive enough telescopes. But if they have scattered, they could be too far apart and too faint to track. They would become invisible, lost in the vastness of space. One thing we can be fairly sure of is that 3I/Atlas, or what is left of it, is moving away from the Sun now. It is heading back out into the cold of interstellar space. Decades from now, it will cross the outer edges of our solar system. Centuries from now, it will be far beyond the reach of any spacecraft we could send. And eventually, after thousands or millions of years, it might enter another star system, beginning the whole process again. This brings up an exciting thought. If 3I/Atlas came from another star, then objects from our solar system might travel to other stars too. Comets from the Oort cloud, a distant shell of icy bodies surrounding our Sun, can sometimes get knocked loose by a passing star's gravity. Those comets might be flung out of our solar system entirely, becoming interstellar wanderers themselves. Right now, at this very moment, a comet from our solar system might be visiting some distant alien star, and creatures there, if they exist, might be studying it the same way we study 3I/Atlas. Let's take a moment to recap what we have talked about so far. 3I/Atlas is a suspected interstellar object discovered in late 2024. It showed signs of comet-like activity at first, with a glowing cloud around it. But it faded much faster than expected, leading scientists to think it might have broken apart or been more fragile than typical comets. The question of whether we are tracking the original object or just a cloud of fragments, a decoy, is still being studied, and because it is moving so fast and is now very faint, getting more data is hard. Now let's talk about the bigger picture. Why do scientists care so much about interstellar objects? Why spend so much time and effort studying something that is just passing through? The answer is that these objects are messengers. They carry information about other star systems, places we cannot visit with our current technology. By studying interstellar visitors, we learn about the conditions around other stars, the types of materials that exist elsewhere, and the processes that shape planets and comets in other parts of the galaxy. Every star forms from a giant cloud of gas and dust. When a star is born, leftover material swirls around it in a disk. Over time, that material clumps together to form planets, moons, asteroids, and comets. Each star system goes through this process, but the details can be different. Some systems have lots of water ice, others have more rock. Some form giant planets close to the star, while others form them farther out. By examining objects from other systems, we can compare them to objects from our own system and see what is the same and what is different. 3I/Atlas gives us a chance to do that comparison. If we can figure out what it is made of, we can compare its composition to comets born around our Sun. Are they similar, or are there big differences? Do interstellar comets have the same kinds of ice and rock, or are they made of different stuff? These questions help us understand how common certain materials are in the galaxy, and whether the processes that formed our solar system are typical or unusual. One of the things that makes 3I/Atlas interesting is its behaviour. It acted like a comet, producing gas and dust, but it faded in a way that is unusual. This could mean it is structurally different from comets we're used to. Maybe comets from other star systems are more fragile. Maybe they have been damaged by cosmic rays, high-energy particles that zip through space and can slowly break down materials over millions of years. If 3I/Atlas spent a long time drifting through interstellar space, cosmic rays might have weakened it, making it more likely to crumble when it got close to the Sun. Another possibility is that 3I/Atlas formed in a colder environment than our solar system's comets. If it came from a star system where the temperatures were even lower, it might be made of ices that are more volatile, meaning they turn into gas at lower temperatures. When it entered our warmer solar system, these ices might have vaporized quickly, causing rapid changes and making it hard to study. Scientists are also interested in the shape and size of 3I/Atlas. From the brightness measurements, they estimate it was probably a few hundred meters across, maybe the size of a few football fields. That is small compared to planets, but for a comet, it is a decent size. If it broke apart, each fragment would be much smaller, perhaps only tens of meters across. Objects that small are incredibly hard to detect from Earth unless they are very close or very bright. Now let's think about the path 3I/Atlas took through our solar system. It did not come close to any planets, it stayed relatively far from Earth, Mars, and the other inner planets. This is actually a bit of a shame from a scientific standpoint because if it had passed closer, we could have studied it in more detail. Closer objects appear brighter and are easier to photograph. But space is big, and the chances of an interstellar visitor passing right by Earth are very small. The closest 3I/Atlas came to the Sun was inside the orbit of Mars but outside the orbit of Earth. At that distance, the Sun's heat is strong enough to melt ice, but not so strong that it would instantly vaporize everything. This is the zone where comets usually become active, where the ice starts to turn into gas and the coma forms. For 3I/Atlas, this was the time when it should have been brightest and easiest to study. But it is also when things went wrong, when the fading started and the object became harder to track. Researchers have been comparing 3I/Atlas to the two other confirmed interstellar objects, 1I/Oumuamua and 2I/Borisov. Let's talk about those for a moment because the comparisons are helpful. 1I/Oumuamua was discovered in October 2017. It was the first confirmed interstellar object, and it was strange in many ways. It did not look like a comet. It did not have a bright coma or tail. It was just a dark, rocky or metallic object shaped oddly, maybe like a cigar or a pancake. Scientists are still arguing about its exact shape. Oumuamua moved through the solar system quickly and left before we could study it much. It is now far away, heading back into interstellar space. 2I/Borisov, discovered in August 2019, was different. It looked exactly like a comet from our solar system. It had a bright coma, a tail, and it behaved the way we expect comets to behave. Scientists were able to study it in detail and found that its composition was similar to comets born around the Sun, though there were some small differences. Borisov stayed bright and active for months, giving researchers plenty of time to gather data. 3I/Atlas falls somewhere between these two. It showed comet-like activity at first, like Borisov, but then it faded and became hard to track, a bit like Oumuamua. This in-between behavior is part of what makes it so puzzling. It does not fit neatly into a category. It is its own mystery. One question scientists ask is whether 3I/Atlas, Oumuamua, and Borisov are common examples of interstellar objects, or if they are unusual. Are there thousands of objects like these drifting through the galaxy, with a few passing through our solar system every few years? Or are these visitors rare, with gaps of decades or centuries between sightings? The answer depends on how many interstellar objects are out there and how often their paths cross ours. Current estimates suggest that at any given time, there might be a few interstellar objects passing through the inner solar system, but most are too small or too dark to see. We only detect the ones that get close enough or are active enough to stand out. As our telescopes improve, we should start finding more. In the next decade, new survey telescopes will scan the sky more thoroughly, and scientists expect to discover many more interstellar visitors. Each one will add to our understanding. Here is another interesting point. Some scientists think that interstellar objects might carry organic molecules, the building blocks of life. Comets from our solar system have been found to contain complex organic compounds, including amino acids, which are used to build proteins. If interstellar comets also carry these molecules, it raises the possibility that life's ingredients are common throughout the galaxy. Maybe the chemicals needed for life get spread from star to star by comets and asteroids, seeding planets everywhere. 3I/Atlas might have carried such molecules, though we will probably never know for sure since we did not get a chance to study it up close. Let's talk about the future. What happens next in the study of 3I/Atlas? Right now, astronomers are still analysing the data they collected. They are writing papers, running models, and debating the results. Some researchers are searching for any remaining fragments, hoping to spot a piece of the object that is still bright enough to see. Others are looking at older data, checking if 3I/Atlas was visible earlier than anyone thought. There is also interest in planning for the next interstellar visitor. Scientists want to be ready. They are designing rapid response systems that can alert telescopes around the world as soon as a new interstellar object is detected. The idea is to get as many observations as possible in the first few days and weeks, before the object fades or moves too far away. Speed is important because these visitors do not stick around long. One of the dreams in the space science community is to send a spacecraft to intercept an interstellar object. Imagine a probe that could fly alongside 3I/Atlas, or the next visitor, and take close-up pictures. It could measure the surface directly, maybe even land on it or scoop up a sample. That would give us far more information than we can get from telescopes on Earth. But launching such a mission is very hard. Interstellar objects move fast, and catching up to one would require a lot of fuel and precise timing. It is not impossible, but it would be expensive and require years of planning. Some engineers have proposed keeping a spacecraft ready on standby, fueled and waiting in orbit, ready to launch on short notice when a new interstellar object is found. It is a bit like having a fire truck ready to go. The moment the alarm sounds, the truck races out. In this case, the alarm would be the discovery of an interstellar visitor, and the spacecraft would race to catch it. Whether this will ever happen depends on funding, technology, and international cooperation, but it is a goal that many scientists support. Now, let's think about the name. Why is it called 3I/Atlas? The 3 and the I are clear, third interstellar object, but Atlas refers to the telescope system that found it. It is common practice to name objects after the telescope or survey that discovered them. For example, Comet Hale-Bopp was named after the 2 people who discovered it independently. Comet Neowise was named after the spacecraft mission that found it. So 3I/Atlas honours the Atlas project, a system funded to protect Earth from dangerous asteroids but also capable of spotting these rare visitors. There is something poetic about that. A system designed to watch for threats also finds wonders. While Atlas scans the sky for rocks that might hit us, it stumbles upon travellers from other star systems. It reminds us that when we look outward, we never know what we might find. The universe is full of surprises. Let's wrap up by revisiting the big question. Have we been tracking a decoy this whole time? The honest answer is we do not know for sure yet. The evidence suggests that 3I/Atlas might have broken apart, and if that is true, then yes, what we tracked in the later stages might have been fragments or a dust cloud rather than the solid nucleus. But there is still a chance the nucleus is out there, intact but too faint to see. More observations and more time will help settle the question. What we do know is this. We found an object from beyond our solar system. We watched it change and fade in ways we did not fully expect. We learned that interstellar visitors can be fragile and hard to study, and we were reminded that space science is full of mysteries that do not always have quick answers. Sometimes the most interesting questions take years to solve, and sometimes we never get a perfect answer at all, but that is okay. Science is not just about finding answers. It is also about asking good questions, gathering the best information we can, and being honest about what we do not know. 3I/Atlas taught us a lot, even if it left us with more questions than we started with. It showed us that the universe is bigger and stranger than we imagined, and that even small distant objects can hold secrets worth chasing. So here are the 3 biggest takeaways in plain speech. First, 3I/Atlas is most likely the third interstellar object ever confirmed, a visitor from another star system that passed through ours briefly. Second, it behaved like a comet at first but faded much faster than expected, possibly because it broke apart or was unusually fragile. And third, studying it has been hard because it became too faint too quickly. but the effort has taught us valuable lessons about what to look for and how to respond when the next interstellar visitor arrives. The journey of 3I/Atlas is not over. Even though the object itself is fading into the distance, the scientific work continues. Papers will be published, debates will happen, new data might emerge, and someday, when another interstellar visitor arrives, we will be a little bit wiser because of what 3I/Atlas taught us. 1I/Oumuamua, the first messenger. Let's turn our attention now to 1I/Oumuamua, the very first interstellar object we ever confirmed. Discovered on October 19, 2017 by astronomers using the Pan-STARRS telescope in Hawaii, Oumuamua changed everything. Before it arrived, we suspected interstellar objects existed, but we had never actually seen one. When Oumuamua showed up, it proved that visitors from other star systems really do pass through our neighbourhood. The name Oumuamua comes from the Hawaiian language and roughly means scout or messenger arriving first. It is a fitting name for something that opened a new chapter in astronomy. Oumuamua was strange right from the start. When astronomers first spotted it, they thought it might be a comet or an asteroid. But as they tracked it and studied it more carefully, they realised it was moving on a path that could only come from outside our solar system. Its speed and direction were all wrong for an object born around the Sun. It was travelling at about 26 kilometres per second relative to the Sun, fast enough that our Sun's gravity could not hold on to it. It was just passing through, on a one-way trip. What made Oumuamua truly bizarre was its appearance and behaviour. Most comets, when they get close to the Sun, develop a bright coma and tail as their ice heats up and turns to gas. But Oumuamua showed no such activity. There was no coma, no tail, no sign of gas escaping. It looked more like an asteroid, a bare rock tumbling through space, but its shape was weird too. From the way its brightness changed as it spun, scientists figured out that Oumuamua was highly elongated, shaped like a cigar or maybe even like a flat disc or pancake. No asteroid or comet we had seen before had such an extreme shape. The length-to-width ratio was huge. Oumuamua appeared to be at least 5 to 10 times longer than it was wide. Picture a football, but stretched out much more. Some scientists think it might have been even more extreme, maybe like a thin shard or a piece of a shell. The exact shape is still debated because we only saw it from one angle, and it was very far away. But everyone agrees it was unusual. Then there was the acceleration mystery. As Oumuamua moved away from the Sun, astronomers noticed it was speeding up slightly, more than could be explained by the Sun's gravity alone. Something was giving it a tiny extra push. For a comet, this would be easy to explain. Escaping gas acts like a little rocket, pushing the comet along. But Oumuamua did not show any signs of gas escaping, so what was pushing it? Scientists came up with many ideas. One suggestion is that Oumuamua was venting gas, but in amounts too small to see from Earth. Maybe it had just a thin layer of ice on its surface, and when that ice warmed up, it released a tiny bit of gas. Not enough to create a visible coma, but enough to give a small push. Another idea is that Oumuamua was made of something unusual, perhaps a kind of ice that we do not see often, like frozen hydrogen or nitrogen. These ices can turn into gas at lower temperatures, and they might not produce a bright coma. A more creative idea, though one most scientists think is unlikely, is that Oumuamua could be artificial, a piece of technology from an alien civilization. Some researchers pointed out that the acceleration could be explained if Oumuamua was a light sail, a thin sheet designed to be pushed by sunlight. If an advanced civilization wanted to send a probe across the galaxy, a light sail would be one way to do it. But there is no solid evidence for this idea. It is more of a thought experiment than a real explanation. Most scientists think Oumuamua is a natural object, just a very strange one. Oumuamua taught us an important lesson. Interstellar objects do not always behave the way we expect. They can be odd shapes, made of unusual materials, and do surprising things. It reminded us that our experience with objects in our own solar system is limited. There are probably all kinds of comets and asteroids out there in the galaxy, and some of them are going to look and act differently than anything we have seen before. By the time scientists realized how special Oumuamua was, it was already leaving. It passed closest to the Sun in early September 2017, before anyone even knew it was there. By the time it was discovered in mid-October, it was already moving away, getting fainter and harder to see. Within a few months, it was too faint for even the biggest telescopes to detect. Today, Oumuamua is long gone, billions of kilometers away. heading out of the solar system and back into the interstellar void. We will never get another look at it. It is a visitor that slipped through our fingers. But the discovery of Oumuamua sparked excitement and determination. Astronomers realized they needed better sky survey systems to catch these visitors earlier, when they are brighter and easier to study. They also started thinking about how to respond quickly when the next one arrives. Oumuamua was a wake-up call, showing us both the potential and the challenges of studying interstellar visitors. 2I/Borisov, the comet that behaved. After the strangeness of Oumuamua, scientists wondered what the next interstellar visitor would be like. They did not have to wait long. On August 30, 2019, an amateur astronomer named Gennady Borisov spotted something unusual while using a telescope he built himself in Crimea. The object was moving across the sky in a way that caught his attention. He reported his observation, and other astronomers quickly confirmed it. They named it 2I/Borisov in his honour, marking it as the second confirmed interstellar object. 2I/Borisov turned out to be wonderfully normal, at least compared to Oumuamua. It looked and acted exactly like a comet from our own solar system. It had a bright coma made of gas and dust. It had a tail that stretched behind it as the pressure from sunlight pushed material away. It showed all the signs of ice melting and gas escaping. In every way, it behaved just as scientists expected a comet to behave. This was actually very exciting. It meant that not all interstellar objects are weird. Some of them are just regular comets, similar to the ones born around our Sun. This was reassuring because it suggested that the processes that form comets are probably the same across the galaxy. Stars form from clouds of gas and dust. Leftover material becomes comets and asteroids, and some of those comets get kicked out of their home systems and wander through space. It is a natural process, happening everywhere. Scientists had months to study 2I/Borisov because it stayed bright and active for a long time. They used telescopes all over the world and even the Hubble Space Telescope in orbit. They analysed the light coming from it, breaking it into different colours to see what elements and molecules were present. They found water vapour, carbon monoxide and other chemicals commonly seen in comets. The composition was similar to comets from the Oort cloud, a distant region of our solar system filled with icy bodies left over from when the solar system formed. There were a few interesting differences though. 2I/Borisov seemed to have a higher concentration of carbon monoxide compared to typical solar system comets. Carbon monoxide is a gas that forms when carbon and oxygen combine. The extra carbon monoxide suggests that Borisov might have formed in a colder part of its original star system, where more carbon monoxide could freeze into the ice. This tiny difference gives us a clue about the conditions around the star where Borisov was born. Researchers also studied the size and shape of Borisov's nucleus, the solid, icy core at the centre. They estimated it was about 1 kilometre across, roughly the size of a small mountain. As it travelled through the inner solar system, the sun's heat melted ice on the surface, releasing gas at a rate of about 30 kilograms per second. That might sound like a lot, but for a comet, it is typical. Comets can lose tons of material every day when they are active, and they can do this for weeks or months until the ice runs out or they move too far from the sun. One of the most detailed observations came when scientists used powerful radio telescopes to search for specific molecules in Borisov's coma. They were looking for things like hydrogen cyanide, which is common in comets and helps us understand their chemistry. They found it, along with other molecules, confirming that Borisov's chemistry was comet-like. This kind of detailed study is exactly what scientists wish they could have done with Oumuamua and 3I/Atlas, but those objects did not cooperate. They either did not show activity or faded too quickly. 2I/Borisov also gave scientists a chance to test their equipment and methods. Studying an interstellar comet requires coordinating observations from many telescopes around the world. It means scheduling time on big professional instruments, analysing huge amounts of data, and working quickly before the object leaves. Borisov was a practice run. The lessons learned from studying it will help when the next interstellar visitor arrives. Astronomers now know what works, what does not, and what to prioritise. One thing that struck researchers was how ordinary Borisov seemed. Here was an object that had travelled across light years of space, drifting through the cold darkness for who knows how many millions of years, and it looks just like a comet from our own backyard. It is a reminder that the universe, despite its vastness, follows the same laws of physics everywhere. Chemistry works the same way around every star. Gravity behaves the same. The ingredients for making planets and comets are similar from place to place. We are all connected by the same set of rules. 2. I/Borisov reached its closest point to the Sun in early December 2019 and then began its journey outward. By mid-2020, it was fading as it moved farther away. But unlike Oumuamua, which disappeared quickly, Borisov stayed visible longer, giving scientists plenty of time to collect data. By the time it finally faded beyond detection, researchers had gathered enough information to write dozens of scientific papers. It remains the best-studied interstellar object to date. There is something hopeful about Borisov. It shows us that not every interstellar visitor is going to be a mystery that slips away before we can understand it. Some will stick around long enough to be studied properly, and as our technology improves, we will get even better at this. Future telescopes will be more sensitive, able to detect fainter objects and gather data faster. The more we learn, the easier it becomes to study the next visitor. Now let's step back and think about the bigger picture. What do these interstellar objects, 3I/Atlas, Oumuamua and Borisov, tell us about the galaxy? Why does it matter that we are seeing visitors from other star systems? The answers touch on some of the biggest questions in astronomy, and even in the search for life beyond Earth. First, interstellar objects tell us that the galaxy is more connected than we might think. Stars do not just sit in isolation. They interact with each other through gravity. When two stars pass relatively close, their gravitational pull can disturb the comets and asteroids in each other's systems. Some of those objects get flung out into interstellar space. Over billions of years, this process has filled the galaxy with wandering comets and asteroids, all drifting between the stars. Some estimates suggest there could be trillions of these objects spread throughout the Milky Way. Every so often, one of these wanderers passes through our solar system. 3I/Atlas, Oumuamua and Borisov are just the ones we happen to notice. There are probably many more that pass through without being detected, because they were too small, too dark, or moving at the wrong time. As our detection systems improve, we expect to find more. Some scientists think we might discover several interstellar objects every year within the next decade. Each discovery is a chance to learn about other star systems. By studying the composition, structure, and behavior of interstellar visitors, we can piece together what conditions are like around other stars. Are the materials similar to ours, or are there differences? Are comets common everywhere, or are they rare in some systems? Do all star systems make planets, or do some skip that step? These questions help us understand not just our own origins, but the entire process of how stars and planets form across the galaxy. Interstellar objects also offer a tantalizing possibility when it comes to the search for life. Scientists have found that comets and asteroids in our solar system carry organic molecules, the carbon-based chemicals that are the building blocks of life. Amino acids, the pieces that link together to make proteins, have been found in meteorites that fell to Earth. These meteorites came from asteroids in our solar system. If our comets and asteroids carry life's ingredients, then it is reasonable to think that interstellar comets might carry them too. Now imagine this. A comet forms around a distant star. It gets knocked out of that system and travels through space for millions of years. Eventually it passes through another star system, maybe ours, maybe one with planets that have liquid water and the right conditions for life. If that comet breaks apart or gets captured by the star's gravity, pieces of it could fall onto a planet. The organic molecules it carries could seed that planet with the chemicals needed for life to start. This idea is called panspermia, the idea that life's ingredients, or even simple life forms, might spread from place to place on comets and asteroids. We do not know if panspermia actually happens, but interstellar objects make it possible. 3I/Atlas might have carried organic molecules. Oumuamua and Borisov might have too. We did not get a chance to check, but future visitors could be studied more carefully. If we ever find complex organic chemistry on an interstellar object, it would be a major discovery. It would show that the building blocks of life are not unique to Earth, or even to our solar system. They might be common throughout the galaxy. Another big question is whether interstellar objects are just comets and asteroids. Or if there could be something more unusual. Could there be objects made of materials we have never seen? Could there be frozen planets, rogue worlds that were kicked out of their home systems and now drift alone through space? Could there be as some have speculated artifacts from other civilizations. Most scientists think the last one is very unlikely, but it is not impossible. If an advanced civilization wanted to send probes across the galaxy, those probes might look like asteroids or comets from a distance. We would need very close observations to tell the difference. The point is, interstellar objects open up possibilities. They remind us that the galaxy is not empty. It is filled with material, with wanderers, with remnants of ancient star systems, and maybe with surprises we have not imagined yet. Every time we spot one of these visitors, we get a little closer to understanding the full story of the cosmos. Thank you for taking this journey through the mystery of 3i/Atlas and the world of interstellar objects. We have learned that these visitors are rare, strange, and full of surprises. We have seen how hard it is to study something so distant and fleeting, and we have thought about what these objects teach us about the galaxy we live in. The story is not finished. More visitors will come, and with each one we will learn a little more. The universe is vast, ancient, and full of wonders, and we're just beginning to explore it.